Okay, so next, let me move on to how I implement a trick like this using the kind of circuits ideas that we have talked about. So just to refresh your memory again, this is my IV curve and focused on a small segment, and the small segment is at an offset capital V, capital D, a capital I, capital D from the origin. And then what I did is that I applied my input voltage here, a small input voltage that I call small v, small d, and that's as small as small v, small I. And by doing so, I was able to get a linear response in ID. And let me mark that here. And this would be my small I, small d, and that would look something like this. Okay, I got a small sinusoid out there for ID corresponding to the meandering of small d, VD across about the point capital VD and capital ID. And again, VD this is the same as capital VI. Okay, I'm just using VD and VI equivalently. So let's go ahead and implement this in circuits. So here's the key again. The idea is to boost and shrink. I have shrunk my signal of interest. Okay, VI was my signal of interest. I've shrunk it to a small value. If it's a big sinusoid, I've shrunk it to a small value. And then I've added a DC offset to it that I call capital V, capital I. And together, by boosting it and shrinking it, I've managed to articulate or managed to make the signal expose that small piece of the segment of the IV characteristic of the nonlinear device. All right, so now let me go ahead and implement this boosting and shrinking business. Okay, how do I do that? So let's take a look at this circuit up here. And this circuit has my nonlinear device, the LED. Let me just mark that as before. That doesn't change. This is my nonlinear device, and this is my circuit. And in this particular circuit, this continues as my ground node. This is VD, and so where previously I had a input VI, what I'm going to do is the following. So notice that up there I had a input VI, okay, and that input was connected to the circuit, and that gives rise to a nonlinear response. So what I'm going to do now is the following. Now I'm going to change this and break it up into two parts. I'm going to break it up into a DC value capital VI and a small signal small VI, and in this case it's time varying. It's a music signal that I want to transmit, so it's VI of t. So in a circuit sense, the way I can do this is I can apply a DC source here, and by applying a DC source, that gives rise to the boosting of the signal to the point that I care about. And then I'm going to put another source in series here with it, and that is my small VI. Okay, so small VI is a small AC source in series with a large DC VI source. So if I were to draw it, if this is my time axis, and then this is some DC value here, this is VI, this is a DC value. And then for my small signal value, this is 0, this is 0. My small signal value, small VI, I have something that looks like this. Okay, so I've taken a small signal VI and put that in series with a large signal VI DC value, capital V, capital I, and I've built a circuit. So what I've shown you here is exactly the circuit equivalent of this boost and shrink business that I talked about. Now, what happens on the LED side? Notice I had a VD, which was my signal out there, and there's an ID as well. Now, I claim that the following is true, and we will look at this in a lot more detail later. Notice that VD is simply given by VD, which is the total signal, is given by really a capital VD plus a small VD by construction. I made that construction. Okay, and so this is the same as VI being equal to capital V, capital I plus small VI. Okay, that was by construction. Okay, these were the same voltages. Now I claim that the current ID will also look similar. The current ID will have a DC value ID plus a small signal value, small I, small d, that will correspond to the capital VI and small vi applied at the input. Now, graphically, that makes sense. If you go back to this graph on the left-hand side, notice that there is a DC offset ID, which is a DC value corresponding to VD, and then there is a small ID about that point. Okay, so graphically you can see that, and I'm going to mark that down here. And we will look at that mathematically as well. Okay, so this is how I implement this trick. Okay, this is how I implement this trick of a boost and shrink. Okay, just remember boost and shrink. You add a DC value and then you shrink the input. Okay, so if you do something like this, what do you get? So the result is the following. The result is, if I plot things a little bit more carefully here, then this is what I get. Okay, first of all, let me draw out capital VD, which is my DC offset. And then I have a small signal input about the DC offset. And so, that is going to look, something like this. That's a DC value. And notice that about the DC offset, I get a small VD out there. And then notice that at any given point in time, my total signal is small v capital D, which is a sum of capital V capital D plus small vd. Okay, so notice the signal. Vd is my DC offset, and then about that point, I have a small Vd, and together they sum up to the total signal Vd at any given point in time. Okay, so this is my time axis. The current behaves in a corresponding manner, and I get something like this. This is my ID, so let me mark that down. That is my DC offset at the current output. And then I get some ID about that DC point, and that current is going to look like this. And the current also has a small value, small I, small d, and then this is my total signal I capital D. Okay, where I capital D is the DC value plus the small signal value. So my input is VI and my current response is ID. And in this case, the output sinusoid, my current sinusoid is amazingly enough more or less linear. But that is absolutely spectacularly amazing. Okay, where I take a nonlinear circuit, focus on a small region of the transfer curve of the nonlinear circuit, and then boost my input signal so that it meanders about that point. Then what I will find is that my output is going to be more or less linear. Okay, this is an absolutely amazing trick. So what I've covered so far is really a very, very clever and a disciplined way of using a circuit so that we can get more or less linear behavior out of a nonlinear circuit. Okay, really what I've done is I've said, look, I have a nonlinear circuit, right? We are engineers. We can use the nonlinear circuit in any way that we want. And I have this LED device that has some very interesting properties. Okay, it can transmit, it can produce light, a light response in proportion to a light response in response to a voltage applied across it. Okay, it's a very interesting property, but it's a nonlinear device. So how do I use it? Well, what I can do is by imposing this discipline on myself. Okay, if you want, you can call it a small signal discipline, where I'm going to boost the signals to interesting portions of the circuit and then shrink them so they're very small. Then in that disciplined use, I can get a more or less linear response out of this nonlinear circuit. Okay, so this really, really clever and disciplined way enables me to get a linear response. Okay, and this is the small signal trick. Okay, I've been mentioning to you all along in this course that there'll be several aha moments in this course where you will see something spectacular. Okay, some key revelation, and this is one of those moments. This is one of those moments where you've just seen how you can take a nonlinear circuit and by focusing on a small region of operation, you can get a more or less linear response from that circuit. This is absolutely amazing. Virtually every device that we have, the sound amplifiers in our cell phone, the wireless output amplifiers and signal amplifiers and so on in your smartphones, all kinds of music production and video output devices. All of them are generally nonlinear, and the small signal trick is really what is used to make all of these interesting devices behave in a linear manner, so that I don't get a lot of distortion in how I output things. So to really, really convince you, I'm going to do a little demo and show you using sinusoids how these circuits can really give you linear behavior as I boost and shrink my input. Okay, so let's do a little demo and see what we find.